Hey guys, here we go. We're doing 9.1, the questions. But before we get started, I do want to make one quick clarification. So I'm going to go back to the first page. In my last video, I was talking about R, and I also mentioned slope. These things are related, but R is not the same thing as the slope. I do want to make sure you understand that. In fact, in 9.2, we'll talk about how we calculate the slope. However, in this section, we're not talking about the slope at all. Although R is related in this way. If R is negative, then the slope is going to be negative. And if R is positive, the slope will also be positive. But again, R is not the slope. You notice that it can't go on a positive 1, right? But a lot of times you do have a slope that's bigger than 1. So what is R really? R is just telling you how closely your data points are to lying in a line. So if R is equal to 1, that means your data points are in exactly a straight line. If R is very small, it means your data points are just kind of scattered all over the place. Or if R is negative 1, that means also they're in an exact line, and it means it's negative. So your overall slope is going to be negative, but we don't know the slope is negative 1. It's just some negative slope. Okay, that's all the clarification I wanted to make, and we'll see this more as we go. In 9.2, we'll talk about the actual slope, and we can see the difference between the two. Okay, question number 1. Phosphorus is a chemical used in many household and industrial cleaning compounds. Sadly, phosphorus tends to find its way into surface water where it can kill fish, plants, etc. A random sample of 8 sites in a California wetland study gave the following information about phosphorus reduction in drainage water. In this study, X is a random variable that represents phosphorus concentration in 100 milligrams per liter at the inlet of a biotreatment facility. And Y is the random variable that represents total phosphorus concentration, again in 100 milligrams per liter, at the outlet of the passive biotreatment facility. Make a scatter diagram for this data and comment on the relationship between X and Y. Okay, so all that's going on here, you have some data that's X is representing the values as they come into the treatment, right? And if it's a good treatment, then that value should be reduced as it exits. Y is the values of the concentration as the water exits the treatment facility. Now, what are we doing? We're just making a plot of the points. And so the way that you do that, okay, on your calculator, we're going to use the same old function that we used to use. Start with stat. This is the very first thing we did, right? We go to stat, go to edit, and then you're going to make your lists. This time we have 2 lists. The first list is going to be this guy. This is going to be the first column, L1. These 1, 2, 3, 4, 5, 6, 7, 8 values, yeah. And then Y is going to be this second group. Make sure, though, when you make the list that they correspond to each other. So entry 1 in the first list, L1, that should correspond to entry 1 in the second list, L2. Okay, so take a moment to do that. While you guys are doing that, I'm going to do it on my Desmos instead, because I don't know how to show you my calculator without turning the camera off, and I'm not using Zoom right now. I'm using something similar. So what I'm going to do instead is I'm going to show you a different way to do it on the Desmos graphing calculator. So this is Desmos.com. If you just Google search Desmos, this is going to pop up, the graphing calculator. And there's a tab on the top right. You see these 3 lines. If you click on that, it's got a bunch of options. And the option that we're looking for is statistics linear regression. That's what this is all about. This whole section is about linear regression, correlation. Okay, so I'll open this graph. It gives me already a sample. For now, we're not doing the regression line, so I'm going to hide this for the moment. And then it gives you already kind of a template, yeah? As a template of different points that are sort of random. So I'm just going to change their template to fit my values. I'm going to write in my values. And then, yours, if you're using the old calculator, it's kind of going to look something similar to this, right? You have your first list. It's going to be in a column like that. Kind of like this I'm doing now. And 7.0. And then the second one, 3.3. 5.9, 4.8, 4.5, 4.0, 7.1, 3.6, and 6.1. And then just delete these rest. Alright, so the cool thing is here we already have the scatter plot done for us. This is the scatter plot right here. This picture on the right. Let's zoom in a little bit. So again, all the scatter plot is just the plot, the graph of these points, right? Here's for example, 6.7 comma 4.8. Just picked a random one. That's this guy. Right, the x coordinate here, y coordinate, and it's just plotted that point. You see they roughly lie in a line, right? So because they roughly lie in a line, that means we can expect our r to probably be pretty big, pretty close to 1. And it's going up, so r is going to be positive. Okay, looking down here, actually, this is already the graph for it. It does it automatically. This r is the r that we're talking about. This is the same r that's written over here in the notes. It's just already algorithmically calculated automatically for you. So 0.97, that means we have a very strong correlation. Right? It's above 0.7, it's almost 1. So it's very strong. Actually, that wasn't even a question on here though. They didn't even need to know R is. You just want to look at the graph, the scatter plot, and make a comment about it. And so what can we comment about this? Let's see. What is the question again? Make a scatter diagram. Okay, we did that. Comment on the relationship between x and y. Okay, so x and y. X and y. They are linearly correlated, first of all. Or maybe let's say it this way. There is a strong because again r is 0.97, and just by looking at the graph you can see it's strong. They're closely, they're pretty obviously in a line, right? Almost a line. So it's a strong positive because as x increases, y is also increasing, right? Strong positive linear correlation between x and y. Oops, didn't mean to do that. Here we go. Between x, cannot type for what's happening, and y. Okay, that's it. We answered the question. Here's a dot, here's a diagram. Okay, I did say that I was going to show you guys on your calculator too, right? So if you're using the same old calculator, we have our two lists. The next thing that you do, and we're just going to confirm that it matches this picture here, is you're going to go back to the same area that we used before. What we want is, okay, let me find it real quick first. Okay, so what we want is, you know how once we make the list, before we go to stat calc, right? This time we're going to do the same thing. We're going to go to stat and open calc. But this time, instead of picking one variable statistics, I'm going to go down the line where I see linear regression. Oh, I'm sorry. We're just going to look for regression. Not linear regression, although that's something slightly different, but related but different. We just want regression because we're trying to find the R. So click on regression, and actually already it automatically inputs your two desired lists, L1, L2. Make sure at the bottom there's a spot where it says X list. So make sure those correspond to the list that you want. So notice X list. That should correspond to, or let's just say this. X list corresponds to the first list that you want to input, your X values. So yours should look something like this. And then it says a little bit later, Y list. And it says L2, right? So if you want to change these, you can just click on those, and then you can pick from your available lists. And then click on done. Here, as a quick, in fact, just as a quick test, see what happens if you change this to L1 as well. What you should notice is that if they're the same list, then we should have an exact line, right? And in fact, yeah, that's what happens. Your R then becomes 1, which means that all your points lie on an exact line. That's the line y is equal to x. Okay, that's kind of a side note, but let's come back to L1, L2. And then so your graph, it should look something similar to mine. If I include the line in it, it's going to look like that basically. And it's going to show me that my R is equal to 9.700201929 to be more accurate. But roughly 0.97. Okay, guys, let's move on. Next question. Oh man, this thing's got us. Okay, there it goes. Points disappeared for a minute. Okay, next question. For each of the given scatter plots, determine if the correlation is positive, negative, strong, or weak, or if there's no correlation. So letter A. Letter A, there's a positive. Stop it. Okay, there's a positive linear correlation, right? And I'd say it looks like a moderately strong. So, or you could say weak. It's kind of hard to tell based on the points. They kind of look pretty scattered. It's pretty clear that they're linearly related and it's positive because it's going up, right? So positive, without knowing the R, we're just going to kind of estimate. It's probably maybe less than 0.4. Or I don't know. To me, it looks like it might be more than that. So I'm just going to estimate moderate. Or maybe weak. So positive, moderate, or maybe weak linear correlation. Let's just say correlation, because we're only talking about linear correlations in our class anyway. Oh, what the world? Stop it. Okay. Letter B. Stop it. Letter B. Is there any correlation? Looking at the points, you see a faint line, but not really. Overall, it looks like everything is kind of just scattered all over the place, right? There's no way to predict if I was to pick a random x variable where it's going to be. Like in the first one, if you pick an x variable here, I can kind of guess it's going to be around here somewhere, right? Or if I pick one out here, I can guess it's going to be up here somewhere. In this case, there's really no way of telling, so they say there's no correlation. Since there's no correlation, I don't have to worry about it being positive or negative or anything else. Just no correlation. Stop it. Okay, so letter C. Okay, this one's clearly negative, right? Negative. And it's also clearly strong because it looks like it's lying exactly on a line. So negative, strong correlation. And that's all. Just kind of a conceptual question there. Done. Let's move to the next page. All right, which of the following are valid correlation coefficients? I'm just going to write the answer right next to it. Let's do it in red. Oh, how to change my font color? No, that's box. I don't want box. This is background color, I think. Oh, this is the background color. Okay, there we go. So let's write the answers here. This first one, 1.5. Is that a valid correlation coefficient or not? No, it's not. Invalid. Because remember, our correlation coefficient cannot be beyond 1. Okay, the second one. This is a valid because it can be equal to 1, right? This one, it has to be between positive 1 and negative 1, so that is valid. That's okay. And negative 1, for the same reason that positive 1 was valid, this one is also valid. And this one, for the same reason that 1.5 was invalid, this one's invalid. By the way, other valid points could be anything between 0 and 1 or anything between 0 and negative 1. So like 0.5 would be valid. Negative 0.5 would be valid, and everything in between. Okay, which one has the weakest correlation? Or the weakest correlation is the one that's farthest from either 1 or negative 1. A lot of people think that negative 1 is the weakest, but actually this is just as strong as 1, because we're only focused on the absolute value of R when we're talking about strong or weak. So the weakest one is actually 0. Whatever's closest correlation. Whatever's closest to 0, that is the weakest. Did I spell correlation wrong? Why are you doing this to me? Okay, it's okay now. Okay, moving on. Number 4. Two variables have a positive linear correlation. Does the dependent variable increase or decrease as the independent variable increases? Also, the question is kind of like flipped a little bit, right? Like normally you say, does the independent variable increase or decrease as the dependent variable? I'm sorry, does the Dependent variable. Oh no, this is right. This is right. Dependent variable, that's like your x variable, right? So this is like your, I'm sorry, I keep saying this wrong. Okay, let's start this whole thing again. Question number 4. Two variables have a positive linear correlation. Does the dependent variable, so this is the y variable, increase or decrease as the independent variable, the x variable, increases? So if positive, as one goes up, the other goes up. So we're just going to say right here, it increases. Easy. Okay, number 5. Two variables have a negative linear correlation. Does the dependent variable, okay, so again, the y variable, increase or decrease as the independent variable, the x variable, increases. So as x increases this time, y is going to decrease because it's negatively correlated. That was easy. Stop. Okay. Number 6. Which value shows a stronger correlation, 0.8 or negative 0.9? Or this is the same kind of question we're talking about as up here, right? Which one is stronger? The one that's closer to either negative 1 or positive 1. So negative 0.9 is the stronger. Negative 0.9 shows a stronger correlation. All right, number 7. There's a study done a while ago involving strength of fathers and sons. Not surprisingly, researchers found a relationship between the strength of boys and their fathers. So in other words, the stronger the father is, the stronger the boy is, and vice versa. The correlation coefficient in the study was 0.51. What does this indicate about the relationship between the strength of sons and the strength of their fathers? Okay, I actually kind of gave away the answer. It indicates that, well, first of all, there is a moderate linear correlation between the strength of fathers and sons. It also indicates that as the strength of a father increases, the strength of a son can also be expected to increase. Right, positive means as one goes up, the other goes up. All right, number 8. Moving on to the next page. Since the quarantine began, some people, no one in particular, have been playing more video games. This got me thinking, is there a relationship between the average number of hours spent playing video games per week and IQ? The following chart represents, in the following chart, X represents hours spent playing video games and Y represents IQ. And you're tasked with finding a scatter plot and then calculating the correlation coefficient and then interpreting that correlation coefficient. And you know, these directions up here, these are still valid. You're going to do the exact same thing. Go to stat edit, make your two lists, and go to stat calc and make your regression. Now for making the two lists, you have an option here. You can make two new lists, and then just make sure when you go to change these guys, you change these correspondingly. So maybe you make a list 3. And so you're just going to make sure that you pick list 3 and list 4. Or you can just go back and delete your old list. That'll work too. Either one. Either way you want to do it. For me, I'm going to do it in the decimals calculator. You can also use this calculator if you prefer. The only thing is, I'm not sure if your homework questions might ask for more than 2 decimal places, because it looks like this one only gives you 2, which might be an issue. You might have to just use your own calculator. Alright, so I'm going to do some boring work and just enter these lists. You guys are just going to watch me type in the numbers here. 3, 45, 21, 7, 16, 32, and 12. Oh, that wasn't so long. 70, 115, 105, 82, 93, 125, and 88. Just make sure when you guys enter the values that they line up with each other, the corresponding values line up, because these represents data points, right? X1, Y1, X1, Y1, X1, Y1. or x1, y1, x2, y2 if you want to think of it that way. All right. Let's get rid of these extra rows and let's see. So here our data shows that there's a 0.9, R is 0.9013. Oh, wait, it's giving me more. It gives me 4 decimal places, it looks like. Well, I guess the last one, it was 0.9700, so it just eliminated those extra zeros. All right, so 0.9013 to the nearest 4 decimal places. And let's see the plot of that thing. Okay, here it is. It was just off my screen because the values are pretty large. At 3, you're already at 70 here. So looking at it, you can kind of tell that's true, right? Just it's going to be, they're sort of roughly in a line already. Looks like those points are, well, so they're not actually in a line even though it kind of looked like it from far away. They're just really close to being in a line for those 3. And then the rest is kind of roughly in that relative region, right? Relatively linear relationship. Relative linear, it corresponds to this R being 0.9. If you're interested, the slope is 1.17593. We'll talk about this more in the next section, but this kind of tells you like how much one increases as the other increases, by what factor. All right, so create a scatter plot. We did that. Calculate the correlation coefficient. That's just R value, 0.9013. Let's just write that in here while we're at it. 0.9013. And then how do we interpret the correlation coefficient? There is a strong positive linear correlation between hours spent playing video games, this is good news, and IQ. Okay, next one. Last 2 questions of this section. Over a period of years, the population of a certain town increased. It was observed that during this period, the correlation coefficient between X, the number of people attending college, and Y, the number of people in the city, jail, was 0.9. Does going to college cause people to go to jail? So that's the conclusion that you might think. And what might explain this value of 0.9? So 0.9, that's a high correlation coefficient, right? That means your graph is going to look like, if you were to plot it, something like this, where your data points are like roughly in a line. Because this is actually almost exactly the same, 0.9013, just by chance. So is that the case? All right, let's look at the note here. It says, do not confuse correlation with cause and effect. So that's not necessarily the case that going to college causes people to go to jail. There could be what we call a lurking variable. Lurking is kind of scary, right? Like lurking in the background. It's unseen something. It's like hidden, like a shinobi or something. So unseen variables affecting data, but not included in the study. Okay, so what could be a lurking variable in this case? Actually, they kind of gave it to you, right? They gave you one of the potential lurking variables. That is that over a period of years, the population was increasing. So the population was increasing. If the population increases, then you could expect the number of people who are going to college to increase, right? And if the population increases, you'd also expect overall the number of people in a jail to increase. So, first of all, answer to the first question. Does going to college cause people to go to jail? Not necessarily. Let's write our answer in red on this side. For some reason, I'm center justified. Okay, so going to college does not necessarily cause people to go to jail. And you might think of some other reasons why, the increase in college attendance might have caused people to go to jail. But just one example is that the population itself increased. Okay, so going to college not necessarily cause people to go to jail. What might explain the value? The population increase might explain the value. It's a lurking variable. There's one sort of common example that is given for a lurking variable. It's this idea of like a fire, the size of a fire. So like imagine that you have a bunch of firefighters going to different fires, right? And then they say, okay, the more firefighters go to a fire, they notice that there's bigger damage that's caused. And so you might think, okay, that means firefighters are causing more damage. So the more firefighters I send, the more damage results. So then I should send less firefighters. But that's not really what's going on. What's really going on is you're sending more firefighters because the fire is bigger. So then the real lurking variable is the size of the fire. So it's not a cause and effect that sending more firefighters causes more damage. It's just the fact that there are more firefighters at a bigger fire. And if there's a bigger fire, then there's going to be more damage. So the lurking variable there would be the size of the fire. It's kind of like a standard example that they give for lurking variable. I'm not sure if your book gave that or not, I forget. Okay, number 10. A statistical study of soccer in England showed that there was a negative correlation between the number of passes in a possession and the number of goals scored. The national team concluded that a good strategy was to pass less. This is a true story, by the way. What could be wrong with this conclusion? So actually, I took this example from this podcast. It's featured on 30 for 30. Okay, this is just a side note. 30 for 30. They featured another podcast for one episode. 30 for 30 is like this sports documentary podcast, if you're not familiar. They also do videos. What is it called? They have this podcast called Ahead of Their Time. And episode is titled, I think it's called The Long Ball or something. Something like that. Anyway, so in the story, what happens is this is kind of before analytics was really big. And now, nowadays analytics is really big in sports. And when we say analytics, really it's just a branch of statistics. Or at least it's pretty much statistics that you're talking about, right? So there's this guy that he took statistics on his own. He's kind of just like this random dude that he wasn't actually a part of any team yet or anything, but he started just taking his own statistics. He noted that the English teams would, or not just English teams, but teams in general, they would score more on a possession where they had fewer passes. And so he made this conclusion that, that must mean that, passing less is a key to success. And so he eventually became very influential in the way that England played soccer. And they invented this way of playing called the long ball. So you just kick the ball far and just like try to do as few passes as possible in order to score. But it turns out that his statistics was bad because he made this mistake of causation versus correlation. So he thought that passing fewer was the cause of it, but it's actually correlated to some other factors that were unseen, some lurking variables. So to answer the question now, what could be wrong with this conclusion? Okay, so to make a story short, there could be lurking variables. And I don't know, you could just think of a number of things that might be the lurking variable. Maybe there are many more possessions in general. Oops. Or I don't know, could be any number of things that you could think of. But what actually turned out to be the case for this one is that I think this is actually not, I shouldn't really say possession. It's actually in number of passes. It wasn't in a possession actually. It was number of passes in a play. But it turned out that actually, in this particular case, so this actual story. Sorry, the thing just keeps going back and forth. So it turned out actually that longer possessions with more passes led to more goals. And I think the way it worked was that a particular play may have had fewer passes, but overall there were more passes. And so the more passes overall, longer the possession, then that meant more goals. So more overall passes actually was the key. I think the way I worded this question wasn't exactly the way it should have been. It should have been in a play. In fact, I'm gonna correct that on the notes on the website right now. Okay, guys, that is it for 9.1. We're almost done. We're almost there. Okay, guys, I'll see you in 9.2 in like 2 seconds or whenever you're deciding to watch the next video. Shoots.